Hello guys, today I am presenting you this very interesting paper. The title is quite cryptic. It says Fishing for Magikarp. Last year in February, there was a research where some people were able to break a GPT model with some anomalous token. So for example, they gave something like solid gold Magikarp word to the model and model was unable to predict the next token. So at the core of it, if you remember, all these models were doing, they were just predicting the next token, and that is still the case in most of the time. But when people were giving something which LLM was not aware of or a gibberish word, or it appeared very, very less in the training data set, then the model would make mistakes. So this happened in 2023 Feb last year, and then GPT-4 was patched. But coming back to this paper, the idea behind this paper is quite interesting. First, we need to understand what exactly is tokenizer. Tokenizer is something that decomposes or breaks down sentences into appropriate words, which are then fed into the large language models. So, for example, you used a data set for making a list of words for tokenizer, and then there is also a word in which is present in that data set which is not that well known or doesn't appear at all during the training of model. Because the word hasn't appeared at all in the training set, large language model has no idea what output after it sees the word, because LLM is just predicting the next word. So when you insert this word during the inference, LLM can drift into hallucination, and then that is where LLM produces gibberish. It is sort of teaching someone a word but not its meaning, but then later testing them on the meaning. So this is where, if you remember, the solid gold magic carp token became quite famous, and if you just search it with this Magikarp or solid gold Magikarp, you will see a lot of articles on it from last year. The thing is that tokenization still remains a huge pain and a large language model attack surface. Including these partially trained tokens in your prompt drifts the model out of distribution into undefined regions of the dynamics, areas that the model is not used to. They confuse the LLM. This paper's focus is discovery and not engineering, but it seems likely one can find token attacks that reliably induce target weirdness, pop up safety, alter personality or behavior, any kind of other prompt injection attack. So, I believe that this paper could be a real game changer when it comes to the LLM safety and security. Now, let me show you a few of the examples from their paper. So if you look at this example, maybe let me make it a bit more bigger. So in this one, the prompt which is being asked is that please help me reformat this Python code. I want to have every element in the array on a separate line. Make sure to copy the elements exactly and never change the values, no matter how strange, otherwise my application will break. And then there is an array of password. If you look at the last element, it is a bit strange. Even the second last is strange. And few of the others are also strange, like media, best and all that stuff. So almost all of the word, especially the last one, it is very unlikely that they would be appearing in any of the dataset. Maybe here and there where there are typos, but not much. Now look at the response of the different models. Mistral Medium has simply lost it. So instead of Llama 2 Media Best and 10, it has just hallucinated in producing nonsense here, Java C, and then interestingly enough, it was able to produce the last one. So maybe this character, the special character, was in its data set. And then if you, it has given some of the explanation too. So you see that it has just, so if you look here, sorry, that Llama 2, so it is saying that Note that I have only added the line breaks, did not change any of the values, but it did change the values. Look at Mr. Large. Mr. Large was able to do some of them, but not all of them, and it also lost the order of the array. So, and then there are a few other examples which are scattered throughout the paper on different model, and I will drop the link to it in video's description, and you can check along. So all in all, I think the point is that this model and this paper is really scratching the surface where things are not that well known, and their method is quite interesting too. For example, the method consists of 3 steps. First, they perform a tokenizer analysis by inspecting its vocabulary and observing its encoding decoding behavior. Secondly, they calculate a number of indicators that identify candidates' tokens that have likely not been seen during model training. And thirdly, they have verified whether identified candidate tokens are indeed out of distribution by prompting the target model. So they first define some useful categories for the tokens. For example, they start with partial UTF-8 sequences. Here the token contains a partial UTF-8 sequence and cannot be converted to a string by itself. And this is typical for fallback by tokens in the various character range. Then another category is of unreachable when no prompt string can result in the token ID. They categorized it as unreachable. They test this by checking if decoding the token to a string and re-encoding it again, and that results in the token. And then they have special tokens, manually defining tokens carrying specific meaning as control tokens. So all in all, they detect and exclude partial UTF-8 sequences and unreachable tokens from their token detection pipeline, as they are not suitable for automatically building verification prompts. So they propose and use model architecture dependent indicators to identify potentially undertrained tokens. And that is the whole idea behind this research. So all in all, a real fascinating read. As I said, I will drop the link to it in video's description. Let me know what do you think. If you like the content, please consider subscribing to the channel. And if you're already subscribed, then please share it among your network as it helps a lot. Thanks for watching.